Okay. All right. So, students, this is a lab. This is the second lab we're going to do. The aim of the lab is to find the acceleration due to gravity of using an inclined plane. So, we have lab 2. And is to find acceleration due to gravity using an inclined plane. We'll also be using a special motion measurement kit. Okay, so basically what we would do, we'll have an inclined plane, and on that inclined plane we'll have some kind of trolley. Some kind of trolley we're going to place on an inclined plane. Okay, so we're going to place a trolley on an inclined plane like this. Some kind of trolley on an inclined plane. Okay, now if the trolley has a mass m, we should know that we have weight acting downward like this. That'll be weight. That weight now can actually be resolved into two components at right angles to each other. Right? By, this is the end of it. We have two components, one like this, parallel to the plane, and one like this. So what happens basically is these two lines meet at 90 degrees. Now, if the plane is inclined at an angle theta to the horizontal, this angle is theta here to the horizontal, and this line should come down here and make the horizontal. That angle should be 90 degrees, which will make the angle here in this triangle, because this triangle actually same angle, right? So this bigger triangle here, we should kind of outline like this. That triangle, wow, that triangle, this angle is 90 degrees, this angle is theta, this angle here and this angle here is the same angle. So the angle up here, this angle here, will be 90 minus theta. So what we essentially have is a situation like this, I have a situation like this, like this. This is the weight. This is the angle 90 minus theta here. So this angle here must be theta. And I'm resolving the weight into two components. I'm resolving the weight into two components. I'm resolving the weight into two components. And two components will be, well, the one opposite, this will be weight sine theta. And this one will be weight cos theta. So effectively, the force of gravity so effectively, the weight which acts downward the weight which acts downward has a component which acts parallel to the plane and that component is actually equal to the weight by sine theta. What you're seeing here, weight sine theta. So the force parallel to the plane then, therefore, the force due to gravity, the full effect of the force due to gravity parallel to the plane will be equal to W sine theta, which is the same as the mass of the object by G by sine theta. Now, it is our objective to find G. So now if F is equal to m times a, the acceleration is always equal to F on m. Therefore, if the force parallel to the plane is equal to mg sine theta, as the force parallel to the plane, therefore and the acceleration parallel to the plane will be equal to the force, which is mg sine theta, all divided by m. It cancels, and therefore the acceleration in the plane is g sine theta. Now we wish to do an experiment to find g. So what we could do, we can take that same object, that's your plane, we take our object, hold it at rest initially, then release it, and basically find the time it takes to pass 2 points. a fixed distance apart. So let's say this distance is S. And let's do better than that. Let's actually carry, while we hold the object at rest, let's use this point as the starting point. Okay? So in fact, the S is from here to here. Yes, the object is at rest initially here. And let's say we're going to release the object from here. We're going to put a mark on the track somewhere here, so that when this is released from rest, right, we'll start a stopwatch. And when it passes that point, we're going to stop our stopwatch. And you know, over this period, the force is mg sine theta, and the force parallel to the plane, the acceleration parallel to the plane will be g sine theta. So I can use now, using equations of motion, eventually start at rest, eventually starts at rest, an object, and also what? Assuming there are no other forces, assuming other forces parallel to the plane are negligible, right, those forces would be like what? Example, friction, right? Drag. We are actually going through air. Assuming those things are negligible, what we should get, we could use the equation of motion that looks like this. We can use S is equal to U times T plus a half AT squared. But we said it starts at rest, so U is 0. So therefore S is equal to AT squared times a half. But you see the acceleration down the plane will therefore be g sine theta. Right, since the other forces down the plane, normally the F total force parallel to the plane would have been equal to the weight component parallel to the plane minus drag minus friction. Drag might be the fluid and friction might be like the wheels at the axis of the wheels. But since these are both 0, we assume them to be negligible. Then F net on the plane is equal to that, and then the only force on it will be the force parallel to the plane, and therefore acceleration on the plane is going to be g sine theta. So I have now, this is now going to be equal to a half into g sine theta times t squared. Okay? Now, let's assume I'm able to, let's assume I'm going to build a table. No, or better yet, let's assume when I release this, keeping this distance fixed, alright, S star is fixed. I adjust the angle. This angle here is varying. This distance is fixed. And the time, the responding time to go between here and here is measured. then what we'll actually have, we'll have, let's make the equation up a bit. Multiply both sides by 2, I get 2 times s as a constant still is equal to g sine theta. Remember, theta is being varied, so sine theta is a variable, right? Times t squared. This is also a variable, that's the responding time. Oh, no, that isn't so helpful. So let me use this then. I could put 2s over sine theta will be equal to g by t squared. Now this is the responding variable. This is the manipulated variable, the angle, because we're in the angle. So I prefer to write it maybe like t squared is equal to 2s on g sine theta. Now t is unknown, so t squared will also be an unknown, a pattern on our y-axis. 2s on g, that'll be a constant because we're keeping the distance constant. So this is like y, this is like m. This comes like, if I put this on the x-axis, x, and looking for c, then I'll have to add 0 here, so c will be 0. So y is equal to so as I said, 0 is understood to be here. So that if I put a graph of t squared against sine theta, so if I decide I'll do a graph of t squared versus sine theta, I expect to get a straight line, a series of points. Now give me a straight line passing through the origin, I don't know. What do you think? So I expect to get a straight line passing through the origin, I don't know. So, if I find the gradient of this graph, the gradient of the graph m will be equal to 2s on g in that situation. Okay, and you go on to find g. So you find g. After you find the gradient, by taking 2 points on the line, you could do that. Take 2 points, 2 non-plotted data points on the line. You find the gradient of that. You find the gradient of that. M will be delta y and delta x, but that will be the constant in the equation here. That will be 2s on g. And that will, if you want to get g, then therefore g will be equal to 2s all over the gradient of your graph. Of course, in your lab you must make mention of a few things. And that is, of course, that the equations of motion could only be employed if well, it actually starts at rest and there's some zero errors to get there. Alright? There's some zero errors because to synchronize the clock to start at t equals 0 when you release this. There's a little zero error there. And then you are actually assuming that F drag and the frictional force is going to be 0. Okay? The frictional force will be 0. This is smooth, totally smooth. And then how it actually works is that your wheels, the two wheels in your trolley, well, the wheels are actually paired. So that's a wheel, it's joined to another wheel on the other side of the trolley. I have a rod going from here to there. That rod joins the two wheels. Okay? But the wheel itself is a little where it's connected there, then there's a little friction right there. So it doesn't allow the wheel to spin well. So this rod here, which goes through here, is a little friction between that rod and the wheel that can actually affect the friction here. Okay? So, that would be the basis of what lab you're going to do. So you're going to basically set up an inclined plane. And the apparatus should look something like so. This is what I want you to do. On this snappy apparatus as shown here, measure the angle theta as the angle here. So you're going to measure this angle here, theta. But the way you're going to do it, you're going to actually hang a plumb bob. Because it's very difficult to measure the angle here. You hang a plumb bob here. It hangs perfectly vertical. And you take your protractor and measure this angle here. That angle will happen to be equal to this angle because it's vertically opposite, as you can see. And this line will come down here and make 90 degrees. So measure this angle, the angle the plane makes with the string. Measure that angle, subtract it from 90, and you'll get the angle theta. So you measure this angle, subtract it from 90, and you'll get this angle here, which happens to be this angle here. You will get theta. You will then, at that angle, find the time it takes for the trolley to travel between this gap and that gap. So the trolley will pass and trip this light gate and then that light gate, pass through that light gate. And that time will be shown up on the QED motion computer. You repeat steps 5 and 6 of the angles, and then you'll do your table up of your results. Okay? And this is how we are going to do this lab. Okay? So your table, right, so you decide the angles and choose angles that are reasonably spaced so you get a nice graph. Okay? I will demonstrate how the equipment works when we reach in the lab. Thank you.